The second derivative test is an alternative to the first derivative test to help determine whether a critical point of a function is a relative maximum or relative minimum. The steps below are as follows. Number 1, find the critical values of the function. Number 2, substitute the critical values into f of x to find the critical points. 3, evaluate f double prime of x at each critical value for which f prime of x is equal to 0. If f double prime of x sub 0 is less than 0, a relative maximum occurs at x sub 0. That's to say, if it's concave down, then we have a relative maximum. Then B says if f double prime of x sub 0 is greater than 0, a relative minimum occurs at x sub 0. So if it's concave up, then we have a relative minimum. And then C says if f double prime of x sub 0 is equal to 0, or f double prime of x sub 0 is undefined, the second derivative test fails, and we need to use the first derivative test. So the second derivative test is nice in that it gives us an alternative to the first derivative test. However, sometimes it does not work, and we need to end up using the first derivative test anyway. So let's look at an example. Example 4 asks us to find the relative maxima and minima and points of inflection of the function y equals 3x to the fourth minus 4x cubed minus 2. So let's go ahead and take the derivative. We have 12x cubed minus 12x squared. And now we want to go ahead and find the critical values. So I'm going to factor out 12x squared, and that will leave us with x minus 1 inside the parentheses. Now we can set that equal to 0. And using the zero product principle, we get 12x squared equals 0 and x minus 1 equals 0. And then if we solve both of those equations, if I divide by 12 and take the square root, here I would get x equals 0, and here I would get x equals 1. So our critical values are x equals 0 and x equals 1. Then we want to go ahead and plug those back into our original function. If we plug in 0, then the output would be -2. So one of our critical points will be 0, -2. And the other one would be 1, comma, let's see, so y of 1 is equal to 3 times 1 to the fourth power minus 4 times 1 cubed minus 2, and that will give us 3 minus 4 minus 2, and that ends up being 3 minus 6, which is -3. So those are our critical points. Now, if we're going to use the second derivative test, we need to take the second derivative. So y double prime is equal to 36x squared minus 24x. And we can plug in y double prime of 0, which would be 36 times 0 squared minus 24 times 0, and that ends up equaling 0. So here the second derivative test fails us, and we get inconclusive results. And we'll need to use the first derivative test for 0, but let's try 1 and see what happens. So y double prime of 1 is equal to 36 times 1 squared minus 24 times 1, which is just 36 minus 24, and that is equal to 8, which is positive. And so at 1, that means it's going to be concave up, and we have a relative minimum at x equals 1. However, again, we'll still need to use the first derivative test for 0. So Let's make our sign diagram. Here's 0, here's 1. If 1 is a relative minimum, then we know that before it's going to be decreasing and then increasing. So at 0, it's either decreasing or increasing. If it's increasing, then we have a relative maximum. So let's use a test number. I'm going to use -1 for our first derivative. So y prime of -1, and that equals 12 times -1 cubed minus 12 times -1 squared, and that's going to give us -12 minus 12, which equals -24. So on this interval from -infinity to 0, that means that our function is decreasing, and then it's also decreasing again between 0 and 1. So that means likely what's happening is that we have an inflection point at x equals 0, but let's use the second derivative to verify that. So if we do y double prime of -1, that is equal to 36 times -1 squared minus 24 times -1, and that equals 36 plus 24, which is equal to 60. So here our second derivative is positive, which means that it's concave up. And then I'll use a test number of 0.5 here. So y double prime of 0.5 is equal to 36 times 0.5 squared minus 24 times 0.5. And let's see, a quarter of 36 is 9, and then half of 24 is 12, so that ends up equaling -3. So that means that this is negative. So if we're going from concave up here to concave down, that definitely verifies that we have an inflection point at x equals 0. So lastly, we just want to kind of do a write-up of our final answer. So we have an inflection point at 0, -2, and a relative minimum of -3 when x equals 1. And that is our final answer.